Superposition of waves is another way of saying we're going to study how waves add, or addition of waves. Now, we all know that 1 and 1 make 2 most of the time, and we're pretty used to that kind of very simple arithmetic of how things add. And yet, waves do some interesting things in terms of how they add. 1 and 1 doesn't always make 2. Sometimes it makes a number like 0 or less than 2. So we have to study waves carefully because they have some really interesting properties in terms of how they add together. Superposition is again just addition of waves, so we're going to be looking at the same old idea where we take two wave functions and add them together. Except when we add waves together, they do some interesting things. They pass right through one another as they're traveling along, and for the brief moment that they overlap, they do add. But it's not just as simple as they're always positive, because as we know, sometimes waves are positive with respect to the transverse displacement or amplitude, and sometimes they're negative, and so that causes some interesting features. They also have another interesting feature in that they pass right through one another. This isn't like colliding billiard balls that deflect off in opposite directions. These two waves that we see on the screen passing right past one another, one is a left traveling wave and one is a right traveling wave, they pass effectively right through one another undisturbed. Now when they overlap, they look clearly very different as a sum than they did as individual wave fronts, but after they've passed through one another, they look undisturbed altogether. There are two categories of superposition that deserve special mention. They again go by the term interference, but sometimes interference, because waves add in the positive direction, can act together, and that's called constructive interference. And sometimes waves are moving in the opposite direction, so that's called destructive interference. We'll see what I mean by that. So let's imagine I have two wavefronts, and they both have a positive deflection upward in the y direction, even as they're traveling, one left and one right. While they overlap, they form a net wave that's shown in green that is the sum of the two. And because both had a positive deflection, in other words, the amplitude was swinging up at the time that they were passing by one another, the resulting net wave that's produced is larger in amplitude than the original two. This could work also if you have the two waves passing by one another that both have their amplitude swinging down. Then the net wave is larger in amplitude, or in magnitude I should say, than it would have been either one separately. Both of these are examples of constructive interference. When the net wave, which is shown in green, is larger in magnitude than either wave initially in the sum, this is what's known as constructive interference. Destructive interference, though, happens when I have two waves, one whose amplitude is swinging up and the other which is swinging down, and during the time that they overlap, the red and blue in this case sum together to make the green. Now, because one has a positive deflection and one is a negative, when I simply sum the two wave functions together, I get 0 in this case, or something that's less than the magnitudes of each of them individually. In this case, when the two waves are oppositely oriented, the net wave can actually be smaller in magnitude than the sum of the two magnitudes, or even as small as 0 in amplitude. This is what's known as destructive interference. An observer actually only sees the individual, does not see the individual waves during the interference pattern. One only perceives the sum. So if this was two sound waves, you would actually hear a deafening quiet. There would be nothing there. And that's kind of remarkable to think about, because this is a case where 1 and 1 don't make 2, 1 and 1 make 0. And it's kind of hard to imagine that we can have two sound waves or two light waves or something added together such that you see 0 out. Of course, after the waves have passed by one another, then they are as they were before, and they don't overlap anymore, so you see the individual waves. Mathematically, this can be seen if we kind of look at what's the form of a traveling wave. So let's imagine that we're summing two waves together, y1 and y2, which both depend on x and t. And let's suppose that y2 is phase shifted a little bit with respect to y1. There's a phase advance. This means that y1 might be a sine kx minus omega t. It's a wave traveling to the right. And y2 would be sine kx minus omega t plus a little bit. To add these, well, this is kind of complicated because we don't know how to add sine functions when they don't have the same argument. But there is a trig identity that we can use, and it's not like you should know this by heart, but I'm just going to cite it here in case it helps make sense of what is about to follow. When you have two sine functions, each with a different angle, theta 1 and theta 2, when you want to add them together, this is equal to twice the sine of the average angle times the cosine of half theta 1 minus theta 2. So that's a trig identity, and we're going to use it now to actually compute the sum here. So the net wave, y of x and t, actually becomes twice the original amplitude, the cosine of half the phase difference, times sine kx minus omega t plus phi. And why does that matter? Well, think about what that this is normally like a traveling wave over here, and so it will still be a traveling wave. And it's got an amplitude that's not just a, but 2a times this cosine right here. And this cosine can be very different depending on what the value of phi is. When phi is 0, I get 2a for the amplitude. That's just like saying I hit these two waves overlapping because phi would be 0. There would be no separation in phase. And that kind of makes sense. When I add two waves that are exactly walking alongside one another, then the amplitude should be larger if I think about that constructive interference case. But when phi is pi, think of what happens to cosine of pi over 2. That becomes 0. And it's like saying those two waves actually cancel one another. This should also make sense because when phi is pi, in this case, then that's equivalent to saying one of these waves is half a wavelength shifted out. And so instead of this red peak occurring right here, the red peak is actually occurring right about here when the blue curve is in a trough. And so that peak cancels that trough, and likewise that peak of blue cancels that trough. So the case of being 180 degrees out of phase is known as destructive interference. The case of being 0 degrees out of phase, that's known as constructive interference.